Hey everyone, so this is the robot that I've built just to learn a bit of ROS and hopefully do some other stuff with. And so far I've just implemented the motor control and the motor encoders, and I've followed the tutorials on Josh Newen's Articulate Robotics, and it seems the tutorials are pretty good. I'll link those in the description, and it seems to be working pretty well. So what his demo does, he has a demo which controls the motors with an Arduino and has the Arduino connected serially to the Raspberry Pi, and the Raspberry Pi is running ros2. What I want to do, and this is the point of this video, is I want to replace the Arduino in that demo with an esp32 and have it connected wirelessly to the Raspberry Pi. So there's two things we have to do. The first thing is we have to implement the motor control and encoders on the esp32, and that's quite simple. And then the other thing we have to do is set up wireless communication between the esp32 and the Raspberry Pi. And I don't really want to be tied with this connector here, with this cable. I don't want to be tied down with it. So this way I can have this basically located anywhere on the robot I want, and I get the wireless communication of the esp32. So I've got everything wired up with the Arduino. I haven't added the Raspberry Pi or ROS yet. I'm just testing it with the Arduino to make sure the encoders are working and everything's going in the right direction and that kind of stuff. So I'm using the code that I got off Josh Newen's GitHub, and that's from Articulate Robotics. But I've made a couple of small changes. So here's the code here. So the only change I've made is in the motor driver section, where I've added the cytron motor driver that I'm using, and then I've added some code for the cytron motor driver. And it's actually much simpler to work with a cytron motor driver because it only has 3 pins: a direction pin, a speed pin, and a ground pin. And then the commands are here that we type into the serial input. So I've got it connected to the computer via the serial cable. And so these are all the commands. So O is motor PWM. So let's just go R to reset, and then O, let's say 50-50, which means each motor is going to spin at 50. 50 is the PWM, so 0 to 255. We can see the wheels going forward, and now we can check the encoder values, and they're about equal. One's moving, I guess, slightly faster than the other, 916 and 921. And I think this encoder, this motor has about 770 pulses per revolution, so that's just over one revolution of the wheel. And they're both positive, which means that we're going forward. So that means it's wired in the right direction. That's another reason why you test it before you actually put it on the ground. See, I've got it just mounted up on this Tupperware container, is just to make sure that when the wheels are going in the same direction, you're getting the same value, like positive value for the encoder when they're going forward, and negative value when they're going backwards. And if you're getting a reverse value, you can just switch the pins around, or you can add in a negative sign in the code, whatever you find more suitable. And then the one thing I want to say, when you're running this code that Josh Newen has provided, you need to make sure that in your serial monitor you've got this set to carriage return. If you've got it set to no line ending or new line, it won't work, because the code actually looks for a carriage return when it's running, and otherwise it won't enter the actual function. So we can just type the commands from here, and when Josh does it in his video, he has it connected to the Pi. But it's always better to do it like one small step at a time, just to make sure that there's no bugs or bad connections. So I've got the demo working now from Articulate Robotics with the Arduino, and it's basically for the motor, that is the demo for the motor. So it basically has this this GUI, and you can set the speed of the motors, the left motor and the right motor, and you can also set the number of revolutions as well, revolutions per second. So here, let's do this, 0.4 and minus 1.1. Okay, so that's pretty good. So let's... Alright, so now that's all working. The next thing I need to do is I want to transfer it all to this esp32, just so I can have it all communicating wirelessly. So before I continue, I'm just going to give a quick overview of the robot chassis. So it's basically two layers. So the base layer here is made out of this robotics channeling, and I followed the instructions from the DroneBot workshop video to build this base layer. And on the base layer, I've just got the motors, the 12 volt DC motors, which are these yellow jacket motors. The ones I'm using, I don't think they make those anymore, but you can get very similar ones off the Survey City website. And I've got these terminal strips. I've got three, one for 5 volt, one for ground, and then one at the back there for 12 volt. And I've got a converter, which is a 5 volt converter. So 2 batteries, 2 3-cell lipos, which are around about 12 volts. And one goes through a converter to get to 5 volts, and one's connected directly to the 12 volt terminal strip. And it won't always be 12 volt, or depending upon how well charged it is, but it's just driving the motors, so it doesn't have to be exactly 12 volts. And it's also going through a motor driver, so there will be a slight voltage drop. And then on the top layer, which is just got made out of like this colored bit of perspex that I got from the hardware store, and I've got these bolts here holding it on. You can also use standoffs as well, like copper standoffs or something, but I found these bolts at the hardware store and I thought they'd be really good. And then I've got terminal strips. I've got 3 again, which are connected to the terminal strips at the bottom. And I've got like these little plugs here, so I can easily, this unplugs quite easily. And I can easily take off the, that's the one for the motor, but there's ones for the other motor and for the terminal strips. And so I can easily just take off this top layer and work on the base layer. So the base layer is just for the power, and then the top layer is for the electronics. So I've got the Raspberry Pi at the moment, esp32, but I had the Arduino on here, and the 2 cytron motor controllers. And then I can add more electronics up here as I go, and I can also add more layers. So I'm actually going to put the Raspberry Pi on an upper layer, and I'm going to put a RP LiDAR there. So I'll link the DroneBot workshop build in the description, and you can get more details from that. So the first step involved in getting everything working on the ESP32 instead of the Arduino is to set up some wireless communication between the Pi and the ESP32. So there's 2 pieces of code for that. One piece of code which is the sketch that goes on the ESP32, and then a bit of Python, a Python script for the Raspberry Pi. So this is the sketch that I've got running on the ESP32, and I'll just take you through that quickly, but I will put this up on my repo as well. So this is the static IP address, which is going to be hard-coded in the Python script. And if you can think of a better way to do that, please put that in the comments. And the asynchronous web server, which is going to handle requests from the Raspberry Pi. So when a request comes in from the Raspberry Pi, it comes in like this, where the var is equal to variable. So that's like the variable name, and this is like the variable value. And it might not always have a value. It might want to return a value, but I can handle that in the code as well. So basically, I just get those. I just query those in variable and val value, and then I print that out to the serial monitor as well, just for debugging purposes. But I can put so for this demo, a lot of the variables that it sends are like 2-dimension, one for the left motor and one for the right motor. So I formatted it like a string, like integer underscore and then integer, so I can just read it straight from the, and you'll see that in the Python script, I can just read it into these args straight from the string, straight from the val value string, which is this one here. So it might be something like 10, 20 as a string, and then I'll just, and then this line here will just read it into arg1 and arg2. So the next thing I do is this is my that's my string for my response, and I check what the variable is. So if it's O, I just return the original arg plus 10 and the original arg plus 100. So this is the argument in the request. So that would be, for this one, that would be 10 and 20. So I would return a string with 20, 10 plus 10, and 120. So the return value, if the variable was O, the return value would be a string like this. And that's just for debugging. And now this one here returns a string with the two, with temp1 and temp2. And temp1 is the milliseconds at the start of the function, and temp2 is the milliseconds at the end of the function. So this I can use for timing, which is actually quite useful if I want to see how long all this stuff took. I can use it for timing. So now when I set it up, this is just to set up the static IP, all this code, and I think I got that off Random Nerd Tutorials. And then this one here just registers the handle request function with the asynchronous web server, and then there's nothing in the loop because the asynchronous the web servers generally run kind of as a separate task on their own. So that's the esp32 sketch, and now I'll take you through the Python sketch, which is on my Raspberry Pi. Alright, so I'll take you through the Python code. So the first thing I do is I define the URL, and this is the static URL I've set for the esp32. And then I just define a couple of variables, just a couple of dummy variables to send to the esp32. And this is the string for the request. So it's basically the static URL concatenated with this string here, which has the variable I want, which is E, which returns the timing, if we remember the sketch, and then two integers here separated by an underscore character. So now in the main part of the Python code, I send this string here as a request to the esp32, and I see what it returns. And because it's E here, it should return the timing, the millis. So we expect it to return the millis. So basically I do two calls, a call here and a call here, and I'm doing this because I want to see like how long it is between two calls if I do them in a row. So I'm running that sketch on the Pi, and I'll show you how that works. So this is the Pi here. So I've SSH'd into the Pi, which is Ubuntu Mate Pi, and I was originally going to use Ubuntu Mate, but I didn't end up using that. I'm now using 22.04, and to set this up on the Pi, it wasn't easy. I had to set up the server version, and then from there I upgraded to the desktop version, which was like, I just wanted the desktop because it was a bit easier for troubleshooting. So let's run that now. And so this is my input string to this is my request string here, and then this is my response. So 45 milliseconds and 45 milliseconds. So it basically takes no time to run less than a millisecond to run the function on the ESP32, but then the time between two requests is 45 to 72, which is about 27 or 30 milliseconds. So that's something we've got to keep in mind when we're making requests from the Pi to the ESP32. The time between the two requests is about 30 milliseconds. Alright, so the next thing I have to do is I have to write a sketch on the ESP32 for the motor encoders and let me just move that actually. For the motor encoders and for the motor drivers. So that's a little bit different to the Arduino. I can't just take the sketch straight from the Arduino because the encoders use interrupts, and I'm using quadrature encoder. So I'm going to explain a little bit how those encoders work, and then because that'll make it easier to understand the code, and then implement the code on the esp32. And then I've got to replace the serial connection in the ROS demo that ROS is using with the Wi-Fi connection between the Raspberry Pi and the esp32. And then once I've done that, everything should be working. Okay, thanks. I'll see you in the next scene. This is the specification sheet of the motor I'm working with, and it's the 5202 series yellow jacket. And they don't make this exact one, but they make ones that are quite similar. And it says 223 revs per minute at 12 volts DC. So it's the gear ratio is 26.9, and it says here, this is where you get the encoder stuff. It says here 28 pulses per revolution, which is 7 rises of channel A. So channel A, so there's 2 channels. So channel A will rise, pulse, and then fall down. So for each rise, there's also a fall. So that's 14 changes on channel A and 14 changes on channel B, and that's 28 changes altogether. And the gear ratio is 26.9, which means that the motor is going to spin around 26.9 times, like the shaft will, for every 1 revolution of the motor. So if we multiply 26.9 by 28, we will get 753.2, and that is here 753.2, which is the gear output shaft. So 753.2 pulses per revolution. So if we've got every time a change, an up pulse or a down pulse generates an interrupt on our Arduino or our ESP32, then we get 753.2 interrupts per revolution of the shaft. All right, and I'll draw that out on a piece of paper and I'll show you that in more detail. Okay, so I'm just going to talk a little bit about the encoders. So we have 2 encoders. We have encoder A, all right, and each encoder has, I guess, 7 rises per revolution and 7 falls. So there's like 7 pulses. So we have, let's draw this big. So that's 1 revolution, that's 7 pulses, and this isn't drawn to scale. I had to squash them a bit at the end to get it to fit on the paper. And then we have encoder B. So, and these are quadrature encoders. So quadrature basically means that they're shifted a quarter of a wavelength apart, all right? So 1 wavelength is from here to here. So a quarter of a wavelength means that encoder B will start here, let's say. So it'll go like this, and then like that. So every time it's in the middle, it will, like in the middle of this one, it'll have a transition. So what we do is when we have this transition, when we're going this way, we're going, say, in the forward direction. So we're moving along this way, the wheel's spinning in the forward direction. We have this up transition from here to here. And at this point, we check encoder B, and if encoder B is low, it means we're going forward. And then here, we have another down transition, and we check encoder B for a down transition and it's high. It means we're still going forward. So going forward, for an up transition, encoder B is low, and for a down transition, encoder B is high. And similarly, if we're going forward on encoder B, for an up transition, encoder A is high, and for a down transition, encoder A is low. And then if we're going in the opposite direction, this way, we're moving this way. So this is an up transition now, and so it's a 0 to 1 transition, and we check encoder B, and encoder B is high. And then a 1 to 0 transition, encoder B is low, which means we're going in the other direction. So if that happens, then we decrement our counter. But if it's this case, then we increment our counter, and I've implemented that in the code, and I'll take you through that now. Hey everyone, so I'm going to take you through the esp32 code that I adapted from the Arduino serial code, which I got from Josh Newen's GitHub. And so I've made a few changes, and I've done it in Platform.io just because it's easier because of the autocomplete. So the web server stuff, this file here, has the code for accepting the commands, the requests from the wireless requests from the Raspberry Pi, or whatever you're using for the robot. Doesn't have to be a Raspberry Pi. So there's basically 3 commands that are coming through. One is O. So basically what it does, it gets it reads the variable and the variable value. And there's 3 variables. One is O, which is setting the raw PWM speed on the motor, and the variable values are arg1 and arg2. And that's what it sets as the raw PWM with this set motor speeds function. And the other one is E, and E just returns the encoder values, and then M sets the motor speed. So that's it for the wireless communication, and it's basically the same as the demo I gave before, except with a few bits added. And then the other thing I've done is the motor encoder stuff, which I should show you. So these, I'll show you the setup function first. So I have 4 interrupts. I have 2 interrupts for encoder A and encoder B on the first motor, and encoder A and encoder B on the second motor. So encoder 0 is the first motor, and encoder 1 is the second motor. So A and B on each, and I have 4 interrupt functions, A, B, C, and D, that I add. So every time there's a change on that input pin, input pull up, every time there's a change on that input pin from low to high or high to low, it triggers the interrupt. And so when it triggers the interrupt, so say they're all pretty similar, but say we're on encoder A, when it triggers the interrupt on encoder A, on encoder A for motor 0, then if it goes from low to high, and if encoder B is low, then it increments the value because it means we're going forward. Otherwise it decrements the value because it means we're going backwards. I should also mention that I didn't write this encoder code myself. I took it from James Britton's GitHub repo. So in the next scene, I'll show you the ESP32 working wirelessly with the Raspberry Pi to control the motors on the robot. Hey everyone, so I've got the ESP32 connected wirelessly to the Raspberry Pi now, and I'll just give you a demo. So it's basically the same demo I had with the Arduino when it was connected to the Pi serial port, except now there's no wires between the ESP32 and the Pi, and that's what I really wanted to do. I really wanted to see if I could cut that wire. So first thing, we start the driver node as we did before, and now we'll start the GUI node. And let's drive both motors forward. Okay. Cool, and then one forward, one backwards. Okay, so that's working pretty well. So as you can see, well you can't see, but I'll show you, that the Raspberry Pi isn't connected to anything. It's not actually connected to the ESP32, and they're communicating wirelessly. And really for this, we probably don't even need the Pi. We can probably just run it with the workstation. But the reason I'm going to use the Pi is because I wanted to connect a camera to the Pi, and I could use an ESP32 cam, but I think the Pi is going to give me a better quality image. And also if I want to do like post-processing, like filtering, like any median filtering or average filtering, it's going to be easier with the Pi. And also to connect the LiDAR. So I'm going to go work through the rest of this playlist here from Josh Newen's. So I'm up to here with the motors, and I'm going to put the whole robot together. And if I do something a bit more original that's not in his guide, then I'll try to publish a video on it. Alright, so the next thing I'll do now is I'll take you through the code. This is the code here. I'll take you through the code in the next scene that I'm using to communicate wirelessly between the Raspberry Pi and the ESP32. This is the code that came with the motor demo for connecting the Arduino serially to the Raspberry Pi, and I've updated it to connect the ESP32 wirelessly to the Raspberry Pi, and I'll show you how I've updated it. So the only thing I've had to do is, this is for the driver node, which handles all the communication between the Arduino or the ESP32 and the Pi, and the Arduino or the Pi is driving the motors. That's why it's called the driver node. So it's only this motor driver class that I really had to change. So the first thing I had to do was I had to put in a parameter for the Arduino, for the ESP32 IP, and I'm using this static IP here, and that's implemented in my ESP32 code. And then I had to comment out this connection to the serial port, because nothing's plugged into the serial port or the USB port. So this is going to throw an error if I don't comment it out. And then for this send PWM motor command, so this sends a raw PWM value, which is O. So this is basically equivalent in the serial case to typing O 100 100. Say if you wanted PWM values of 100 at the serial at the motor, so this would be O PWM value 1, PWM value 2. So what I do is I send this command by requests wirelessly to the ESP32. So that's the ESP32 IP, and then this is control, which is how the command handler is implemented on the ESP32, and then O is the variable, and then these are the two numbers separated by an underscore character. So this would be, if they were 100 each, this would just be 100 underscore 100 B val equals, and then this is what it would pull out on the ESP32 side. And then similarly for M, which is the motor speed, and E is the only one that gives feedback, because E gets the encoder values. So, and then I've just redone the response, because the response is in terms of, I guess, it's like a binary response, and I have to change it to UTF/-8 and then split it into two numbers. So that's really basically all I've done. And the other thing is I had to include the mutex here. Otherwise, when you're sending the speed command out, then it tries to send out another command, which is 0. So that's pretty much it. And I'll put this up on GitHub, but if you've got any questions or comments, please leave them in the comments section, and I'll see if I can answer them. But otherwise, hopefully I'll see you in the next video. Thank you for watching.